Hi, this is Yana French, and today we'll be discussing Lab 5, Magnetic Braking with Faraday. Here's our table of contents. We'll start with an introduction, then move into fundamental concepts like applications of Faraday's law, the Biot-Savart law, and Newton's laws. Move into the experimental setup, computational models, the results, and then some discussion questions. The main objective of this investigation is to analyze a set of experimental data and apply Faraday's law relating a time-varying magnetic field to an electric field to a magnet falling through a conductive tube and compare it to a computational model to better understand the behavior of changes in flux and induced magnetic fields. So for preview results, we had the experimental time as 1.254 seconds and computational was 0.891 seconds. One of the fundamental concepts we'll be using in this experiment is Faraday's law, which describes a quantitative relationship between a changing magnetic field and the induced voltage in a circuit in response. We also know that there's proportionality between the voltage and the rate of change of magnetic flux. And we'll also be using the Biot-Savart law, which says that the magnetic field is produced by a constant electrical current, and this is the magnetic counterpart for Coulomb's law involving a vector product with changing distances. And to the right, you can see the equations. We'll also be applying Newton's second law, which is that the force acting on an object is equal to the rate of change of momentum over the period of time, and then Newton's third law, which says each action has an equal and opposite reaction force in the opposite direction. For this experiment, the system is the magnet and the aluminum tube, and the surroundings are everything else, and for the procedure, we located the north pole in the magnet, then we dropped the magnet through a vertical tube just above the opening, and we wanted to time how long it took the magnet to drop through the opening, and we repeated this process to have 5 different measurements, and then we took the average. For this experiment, we assumed that air resistance is negligible, the bar magnet acts as a magnetic dipole, and the only external forces acting on the system is the magnetic and gravitational forces. And then to the right, we have some of our characteristic data, including the magnet's weight, and then the value we used for mu from lab 3, and then we also had the aluminum tube's characteristics. And then on the bottom, you can see our data, and the average was 1.254 seconds. So why can't we use a ferrous tube? Ferrous tubes, by definition, contain iron and are very magnetic, which implies that when the magnet is moving through the tube, the magnet may have more difficulty falling through the vertical tube because of an induced nature. And then what happens to the magnet, and how does this compare to when a magnet is falling in free space without a tube? So the induced current surrounding the magnet will force it to fall slowly through the tube of aluminum foil due to the opposing upwards force. If the magnet was just falling in free space, the object would actually fall much quicker. So for a computational model, this slide basically shows all of the initial conditions and different constants we used in our model. In these slides, we were basically using different physics equations like the magnetic field one and the flux one to find what we needed to put into the model. And then the very last part is basically the force on the ring. So here are results from the computational model, and we can see that the amount of time it took for the magnet to fall through the tube computationally was 0.891 seconds. So for interpretation, what color corresponds to the counterclockwise and the clockwise current? So because we apply Lenz's law, we know that the red is counterclockwise and the blue is clockwise. So what happens if you flip the magnet? The speed of the magnet falling through will actually remain the same. However, the direction of the currents would be opposite because you're changing the north and south. And then how does the real world and computational model compare in terms of time? So we know that our experimental was 1.254 seconds, and then the computational model was 0.891 seconds. So the real world is actually smaller compared to the computational model because in the theoretical data set, air resistance and human errors can be completely mitigated. And then what does the plot shape tell us about the forces acting on the magnet? And the magnet is inside of the tube, which can be seen from time 0.1 seconds to 0.8 seconds. The gravity and magnetic forces are actually equivalent, but before the magnet enters and when it leaves the tube, we can see that the gravitational force is much greater than the magnetic force. So what were some sources of uncertainty? We may have had some human error, so there may have been variance in the distance from where the magnet was dropped from the tube, which could lead to inaccuracies which would make the time change. And then we may have also had issues with stopping the stopwatch at the right time when it hits the hand or when we drop it. And then we may have also had resistance issues like air resistance, which may have led to slower time measurements. And then the magnet may have fallen at an angle, coming in contact with the wall of the aluminum tube, slowing it down. And then we may have had computational errors. So what if? What if the resistivity of the conductor reduced as close as possible to 0? How would the dynamics of the falling magnet change? The magnet would move even more slowly through the tube because of applying Ohm's law. Basically, the resistance decreases, which would then increase the induced current, and ultimately it would lead to a stronger opposing magnetic field. And then what if holes and slots were cut into the tube? How would this affect the ring currents in our model? Slots and holes would cause the magnitude of the induced current to decrease significantly, causing there to be less current rings. Thus, the magnet would fall through the tube at a faster rate than in the tested scenario.